This project is a simple digital combination lock requiring a 3-digit passcode which flashes red on a bicolor LED for the incorrect input or turns green for the correct input. In this case, the code is set to the first 3 numbers of pi, 3, 1, and 4. The digits are selected through a rotary encoder where a clockwise turn increments the digit and a counterclockwise turn decrements the digit with rollovers. Pressing the inbuilt button records the current digit shown where a flash of the LED indicates this. Doing so 2 more times will complete the input combination, whereas pressing the other button resets the combination input in case the user accidentally selects the wrong digit. The project can be broken down into an input circuit and an output circuit connected through an ATmega 328P on an Arduino Nano. The input circuit's main feature is the rotary encoder, previously covered in my lidar measurement device, which presents 2 output pins A and B, both pulled high with pull-up resistors. Inside, grounded plates rest onto the pins when turning the rotary encoder, producing a square wave output on each pin. Turning clockwise shifts the wave 90 degrees forward, while counterclockwise causes a 90-degree shift backwards. These digital square wave outputs, now printed as 1s and 0s, form the gray code counting system, counting forward and backwards for the 2 rotations. This can be visualized by traveling around a unit square positioned in the first quadrant where the coordinates correspond to the outputs on A and B when rotating in a certain direction. The Nano picks up on these values through interrupts, specifically pin change interrupts, which immediately executes code in an interrupt service routine when it is triggered by state changes on the rotary encoder output pins connected to pins 4 and 5. External interrupts, int0 and int1 on pins 2 and 3 are also set up to respond to rising edges caused by pushing the 2 buttons. The rotary encoder pin change interrupts then increases or decreases the digit value presented on the low nibble of port C as a binary value. These pins A0 to A3 are wired to the input pins of the 4511, last used in the grade 10 counting circuit, where it converts binary inputs to 7-segment display mappings that light up the corresponding decimal digit. To accomplish these tasks, the code begins with defines and variables. In setup, the interrupts are set through toggling bits in interrupt registers on the ATmega 328P. Then, ports are prepped for output to control the 4511 and bicolor LED. In the loop, if statements check for the interrupt flag set by the ISRs, which are triggered by the aforementioned rotary encoder and button presses. When set, the code inside executes to change the digit, store the digit, or reset the passcode input. Setting these flags instead of programming these actions straight into the ISR functions is a good practice, as ISRs need to run quickly. Below are some more functions that run special effects on the 7-segment display and bicolor LED to alert the user of their actions. Overall, an emphasis was placed on low-level programming and modular code to maximize efficiency on the ATmega 328P and to provide flexibility in peripheral and program changes. For example, the password length and digits can easily be modified by simply changing the numbers in the array. Here you can see that the original 3-digit pi code still works. By changing the array to include 4 more digits of pi, the user now must enter a 7-digit code. As you can see, the simple one-variable modification is all that is needed to modify the password. By reducing breadth, one can focus on depth, as this straightforward project offered a lot of insight into utilizing the built-in interrupts of the ATmega 328P to provide immediate feedback and free up CPU space. It also allowed me to focus on implementing efficient low-level programming, good coding habits, and practices to get the most out of the AVR microcontrollers.